Okay, so today we'll begin semiconductor diodes, chapter 3. But before I do that, I want to go over the last couple of slides of IC fabrication from chapter 2. Now we rushed through it a little bit, but I want to just do a brief recap, and I do have some show and tell also. So let's. Now in this chapter in EE306, this is basically like 2 or 3 slides, but this is an entire field of study. Okay, chip fabrication is an entire field of study. This is actually my specialization. So my graduate specialization, both master's and doctorate, was in semiconductor fabrication, microsystems, and MEMS. So we are learning about semiconductor devices, right? And we are learning about circuits. Circuits can be of two kinds, discrete and integrated. Discrete would be if you're just buying separate components and putting it on a PCB, which is basically what you do in the lab, right? So you take these components, you build a circuit on a breadboard, test it out. If it works, you mount it on a PCB, and then you're done. And then the integrated circuit design is basically when you take all of those components and instead of buying it off the shelf, you're actually fabricating it on one piece of semiconductor material. Everything is integrated. And that requires a whole different kind of, well, not a whole different kind of, but it requires a slightly different analysis than what we are used to with discrete circuits. So most of this class, yes, we will talk about circuits in a general way, but it'll apply to both discrete and integrated. But one of the reasons we study the, what is happening at the atomic level, like with the electrons and holes, is that devices would behave a little bit differently when it's fabricated directly into a single piece of silicon or a single piece of semiconductor. So that's why we study a little bit of the PN junctions, electrostatics, and then we move on to discrete devices. Okay, so what the analysis that you will study applies to both, and then we'll look at circuits mostly for like discrete, but it also applies to integrated, and then integrator also requires a little bit of separate thinking, which is where the first 2 chapters come into place, come into the picture. So I wanted to show you, this is an actual silicon wafer. I'm gonna pass these around. These are brittle. If I drop them from a height of like 1 inch, right here, if it just falls at a slight angle, it's gonna shatter and break. Okay, so you don't even want to like wave it like a fan. If I do that, wind is gonna break and shatter these. So these are extremely fragile. This is not the reason why I'm wearing gloves, by the way. I have it's extremely dry. That's why I'm wearing it. So you can safely handle those. There's no harm in doing that. And these are actual fabricated wafers that we build here on campus. Okay. So for those of you who are online, I'm going to show it here. If you can see it, these are actual devices that students build in the Cal Poly clean room. Okay. This is a class that is offered only once a year in the winter quarter. It's being offered right now. And so students can actually take the class, go into a semiconductor fabrication facility on campus and build their own devices. Now, that class is under BMed, so it's BMed 435, but it's cross-listed with EE, so it's EE 473. The lecture class is EE 423, and the lab class is EE 473. So in the lecture class, you learn about the basics of semiconductor fabrication. And then in the lab, you actually get to handle wafers, work with dangerous chemicals, and create diodes and resistors and other micro devices. So the class wafers actually have diodes and resistors in them. Okay. The reason I'm passing these around is it's hard to actually relate the illustrations and the diagrams that you see on the slides versus an actual device, right? So each one of those wafers that I passed around, the big one is 6 or 8 inches in diameter, and the smaller ones are used in academic environments, which is 4 inches in diameter or 100 millimeters in diameter, 4 inches or 100 millimeters. And each one of those single wafers can hold hundreds of devices depending on the size. So the end of the fabrication, we slice it all up, and you have tiny pieces which are like probably a couple of millimeters on a side, and then you package it up, and that's the actual microchips that you see in use on a PCB. You see those black caterpillar things with like, not caterpillar, centipede kind of things, which have like pins coming out on both sides. Those are just the packaging. The actual chip is inside it, and it's far smaller than the the length of that device. I mean, length of the packaging. And so each one of those wafers can handle hundreds of devices. And the approach is to build it from the top. So if we look at our slide right here, which I was pointing out, you have, this is the top view. Okay. Looking at it from the top. That's the illustration. This is an actual SEM image. SEM is a scanning electron microscope. SEM image of two contact pads, and your device is right here. And it seems like it's a diode. It could also be a resistor. So this thing is an SEM image. These are just contact pads. Right there. Okay. The contact pads are used to actually make connection to the micro and the macro world, to the world outside, basically. That's why contact pads are the biggest in size. The actual devices are very, very small, but the contact pads are typically big. But anyway, we are building this from the top down. Okay. And a typical 4-inch wafer is about 500 microns thick, only like 0.5 microns, which is the size of the mechanical pencil that we use. Right. So it's very thin, 500 microns thick. And we are barely using the top 2 microns to create our devices. Okay. So in this illustration, we are seeing the top view, and here we are seeing the side view. So I rushed through this at the end of last class. And this is the side view, okay, or the cross-sectional view. So yes. Depends on, so the question being asked is, do the contact pads go to the input and output of a chip? It depends on what and where we want to make the connections. I mean, what kind of circuit it is and where we want to make the connections. If it's a simple diode, it'll go to the 2 ends of the diode. If it's a simple resistor like we have in the the class wafer, it just goes to the 2 ends of the resistor. And so we make connections to the diodes with some probes on a probe station, and we test it out and see if it works or not. So the class wafers have diodes and have resistors. They are not connected to any large circuit. So it goes directly to the terminals of the diodes. If it's a larger circuit, yeah, it could be like power supply, it could be clock input, it could be anything. So in this side view, we can see we are starting with an N-type silicon wafer, and we create an opening and implant or diffuse P-type material into our N-type silicon wafer. Okay. And then we create a further opening to make contacts. And you see these aluminum contacts right there. Obviously, nothing in this image or illustration is to scale. Okay. Everything is magnified and blown up for explanation purposes. So we make metal contact pads. It's separated by an insulating material. The one on the left is connected to the P-type material, sorry, N-type material. And the one on the right is connected to the P-type material. And so those contact pads that you see here in this side view is basically this in the top view. Okay. So there is an insulating material. This is an insulating material. And more often than not, it is simply silicon dioxide. Silicon dioxide is very easy to grow. We simply take our silicon wafer, stick it in a furnace at 1000 degrees C, silicon with an oxygen environment, silicon bonds with the oxygen atoms, and we get silicon dioxide, glass. which is an excellent electrical as well as thermal insulator. Okay. So again, we start with our silicon wafer. Perhaps it's N-type, perhaps it's P-type, depending on the requirement. We create some opening in there. We infuse it with some dopant impurity, and we create a P-N junction. Okay. So this is looking at it from the top. This is looking at it from the side. And when we get in just a few minutes, we'll begin chapter 3. The illustrations that you see in there are not typical of what is actually, how the device is actually built in the real world. But this is something that you should definitely keep in mind. Okay. Once you take this class, which is E306, you are eligible to take the E423 and E473 class next quarter. Okay. So that is an option to keep in mind if you want to go that route. All right, let's get to chapter 3 and let's begin. So diodes. All right. So from now on, we're simply going to use an illustration that looks like this. Okay. It's neither a side view of an actual device, nor is it a top view of a device. We are simply creating an illustration that makes it easier to explain the device physics. So we have a P-type material on the left, N-type material on the right. On a P-type material, the majority carriers are the holes. N-type, it's the electrons, and then minority carriers, of course, vice versa, right? So we have holes on this side and electrons on this side. When we are explaining, typically instructors, when we're explaining this, we say, okay, we created a P-type material, we created an N-type material, and then we bring them together. But that's, again, for explanation purposes. As we just saw in this illustration, it's not as if we are creating two of them separately and then joining using some glue. That's not how it does. That's not how it happens, right? So the moment we infuse a impurity in there, that's the moment when the junction is created. And that junction is illustrated here. This is the P-N junction. P-N junction. Okay. And hence the name of the device, P-N junction diode. The diode, of course, comes from the fact that this device behaves exactly, or I wouldn't say exactly, but very similar to an actual vacuum tube diode. The name is diode, 2 electrodes. So we had a cathode and we had an anode in a vacuum tube. It was a one-way device heated by a filament. And when you applied a positive voltage to the anode, electrons from the cathode would be attracted to the anode. You have a one-way device flowing through, one-way current flowing through the device. So when they came up with a solid-state version of the vacuum tube diode, the nomenclature carried over, and they labeled the positive terminal as anode and the negative terminal as the cathode. Symbols are A and K. I don't know why. I'm guessing C was reserved for Coulomb and for capacitors. So they decided to use K for cathode. Symbol for a diode is a arrowhead with a line at the tip of the arrow. The line signifies that it's the cathode. And on real diodes, this line is typically marked as a band. It's some sort of colored band. The diodes that we use in the lab, the regular silicon diodes, they are black epoxy material, the packaging. It's a small cylinder, and there's a silver gray band running at one end of that material. So it's closer to one terminal, and that terminal indicates it's the cathode. There is a Zener diode in there with a transparent packaging, and the transparent packaging is like a reddish orange packaging, but there's a black band towards one end of towards one of the terminals, and again that signifies that that terminal is the cathode. So keep that in mind when you go to the labs. Okay, so let's see. This is the metal contact right here. And this is the PN junction. It is also known as the metallurgical junction. It's a created junction. And of course, these are the number of acceptor atoms. These are the number of donor atoms. So PP and PN, sorry, PP and NN are basically the donor and the acceptor atoms. So the subscript basically tells you which type of material it is. And then the actual notation P and N is basically the number of holes and the number of electrons. So PP, for instance, is the number of holes in P-type material. The subscript is the type of material. So NN is basically number of electrons in the N-type material. Current always flows from the anode to the cathode. So if I have anode and cathode, when we refer to this device, we always say positive is at the anode, negative is at the cathode, and the voltage is always measured with reference to the cathode. So if we reference diode voltage, if we say diode voltage is 0.6 volts, it means that the anode is 0.6 volts higher than the cathode. If we say diode voltage is minus 10 volts, that means anode is 10 volts less than the cathode. So reference is always positive at the anode, negative at the cathode. Diode current ID always flows from anode to cathode. That is always the reference. If ID is positive, current is going from anode to cathode. If ID is negative, it's going from cathode to anode. Okay. All right, let's take a pause. Let me know if you have any questions thus far. Yes. This one. So in a P-type material, if you are infusing it with acceptor atoms, you have excess of holes. And then you have the electrons, but you have not infused with any external impurities. So the only electrons that are present in the P-type material, assuming there's no other impurity in there, are the intrinsically generated electrons. So I believe your question is an explanation for this equation on both sides, right? Okay, so Ni is basically the product of the intrinsically generated holes and electrons, right? Ni is the intrinsically generated holes and electrons. So that's Ni square. And then this P, of course, is Pi intrinsic plus the external doping. So the number of atoms that you're implanting in there are the only reason why we have the external number of holes. So you divide Ni square by the number of, what do we say, external atoms that come in. It cancels out the intrinsic, and what's left behind is the intrinsic electrons. Okay, and the same thing on the right. There are also take it on a little bit of tangent. There is a higher level course called EE 534, 34 or 24, solid state electronics. So the first two chapters of this book is that entire course, where we go into like a lot of detail with semiconductor device physics and all the equations that relate and govern all these quantities. But I don't think that class has been offered in a while. Anyway, any other questions? Okay. So if we draw a one-dimensional graph, this is the x direction. Actually, it's not quite one-dimensional. X does signify the distance, but I like to call it one-dimensional, because the only quantity in here, if you're interested, is the concentration of the holes and the electrons. And that is in the positive y direction. So number of carriers or the carrier concentration. Okay. At the midpoint right here, that's the junction. That is the junction. And this is going into the N-type material. And this is going into the P-type material. Physically going into the material. What would we expect? We would expect the concentration of electrons will be higher on the N side. The concentration of holes would be higher on the P side. So that is signified right here. Higher level. And then as soon as it crosses over into the P-type material, meaning it going from here to here, the electrons will drop. Same thing happens on the other side. Concentration of holes is higher on the P side, and then the value drops, or the concentration of holes drops when you get into the N side. And in both cases, we are talking about ideal P and N-type material where we do not have any external dopings of the other kind. Okay. If it's a P-type material, we simply say it's P-type dopant, no N-type dopant whatsoever. So the concentration drops as soon as we cross the junction barrier. Okay. That's what that's what this illustration is indicating. And if you draw a line right here, state these are the majority carriers, these are the minority carriers. Okay. So in a P-type material, holes are the majority carriers, electrons are the minority carriers, and in a N-type material, electrons are the majority carriers and holes are the minority carriers. And current flow in these devices takes place due to both electrons as well as holes. And I believe I have stated this earlier. That is the reason why these devices are known as bipolar devices, because the current flow is due to the flow of both positive charge carriers, meaning holes, and the negative charge carriers, meaning electrons. In a BJT, bipolar junction transistor, the word is there itself. In a diode, it's not. But again, current flow in both devices takes place due to both kinds of charge carriers. All right. So if we have, how much time do we have left? 4 minutes. If we have a device which has P and N type dopants, we have a junction in there. Let's look at what happens at the junction itself. We studied about diffusion, or we looked at diffusion earlier, right? Diffusion is when there is a gradient in the concentration of the charged carriers. If there is a gradient, meaning there's a slope, then the charged carriers will diffuse through the material in a bid to even out that concentration or even out the gradient. So this is the gradient in concentration. The charge carriers will diffuse through the material to create something like this. Okay. So they will diffuse through the material. What is that? So if you have a P and N type device, you have excess of holes here. You have excess of electrons here. The holes will diffuse through the junction and keep on going into the N type material, whereas the electrons will diffuse through the junction and go into the P type material. Okay. You got holes on this side, you got electrons on this side, and these are excess, right? These are the ones that are available because of the donor atoms and the acceptor atoms. And so the holes are moving this way, the electrons are moving that way, the opposite direction. Now, if we didn't know anything else about this, which is what the researchers realized, they would have expected that everything would just flatline and there would not be a p-n junction anymore, right? You'd have holes on this side, you have electrons on the right side. If they diffuse until everything is evenly distributed, then there would not be a p-n junction anymore. The junction would be gone because now you have equal concentrations of holes and electrons everywhere. So the junction would disappear. But that is not what happened. What they discovered was that after reaching a certain point, the diffusion would stop. So they had to find a competing mechanism that would oppose that diffusion. Am I making sense so far? Right? Holes and electrons on this side. Concentration of holes is higher on the right. No, on the left. And concentration of electrons is higher on the right. So if holes are higher here and lower here, holes are higher here and lower there on the right. Electrons are higher on the right and lower on the left. The electrons will diffuse from the right to the left, and the holes will diffuse from the left to the right until all hole concentration and electron concentration is equal on both sides of the P and N type junctions. So this diffusion results in a current. That current would keep on flowing until all of the concentration is equal, but that's not what happens. There is a competing mechanism that opposes the diffusion current, and we'll look at that in next class because it's already 12 o'clock. Okay, so we'll end class here today, and I'll see you all on Wednesday. As a question was being asked earlier, is homework due tomorrow? And I said, no, I'll extend it by 1 day, by 24 hours. Yes. So the electron current is shown in the positive direction. It's shown in the positive direction. Yeah. All right, let's see.